So organic chemistry is the chemistry of carbon, and anytime you can form new carbon-to-carbon bonds, it's something that's really special. And so far in this semester, we haven't learned any together. The first way that we'll learn for how to form new carbon-to-carbon bonds are using what are called Grignard reagents. You form Grignard reagents when you have a carbon nucleophile. So a carbon, and it's usually bonded to magnesium with a halogen. Now the halogen is usually bromine, but it could also be chlorine. So either one of those. So that X is standing for a halogen. And notice the trend here, which we saw a little bit with lithium aluminum hydride, is that you have a metal, and this metal has really low electronegativity. And that means that whatever it's bonded to, in this case carbon, has more electronegativity, and so it steals the electrons for itself. Carbon is not an especially electronegative element, and so by bonding it to this metal, we make carbon a nucleophile. And you can create these Grignard reagents just by anytime you have a halogen, chlorine, bromine are the two that'll work most often. Just add solid magnesium, and that'll turn it into this Grignard reagent. And so now, really, you can almost think of that as just a carbon nucleophile there with like a positive MgBr or MgX there. Okay, so that's a Grignard reagent, and that's how we're going to add carbon atoms to carbon chains. It's a huge deal because organic chemistry is the chemistry of carbon. If you can add carbons onto a chain or a backbone, that means you can change the shape of the molecule. And by changing the shape, you change which pockets that molecule can fit into. So in these, a good habit to get into when you look at these synthesis problems is to see if you add any carbons. And if you add carbons, one thing you might have used is a Grignard reagent, especially at this point in the class. Now, what would we react the Grignard reagent with? That depends. Let's say we have our functional group, our new functional group, 2 carbons away. So there's our functional group, Fg for functional group. And here, let's say this is our Grignard reagent, or the carbon that was in our Grignard reagent. If the functional group is 2 carbons away, so 1 and 2, then the way you can make that is by using an epoxide. If, on the other hand, you have your Grignard reagent and the functional group, or the carbon from your Grignard reagent, and the functional group is attached to the same carbon, then you would want to use an aldehyde. So remember, an epoxide is that 3-membered ring. An aldehyde is where you have a carbon double bonded to oxygen, single bonded to a hydrogen. The carbon here is really electrophilic, first because the oxygen is very electronegative, so it's slightly negative, and the carbon is slightly positive, and that's especially the case since they have 2 bonds. But the second reason is because one of these bonds is a pi bond. If you remember, the first bond you ever form between atoms, so like this first one here, comes from the uninterrupted overlap between 2 atomic orbitals. That's a sigma bond. The first bond you ever form is a sigma bond. Every bond after that, so that would be like the second bond here, is formed in this class by parallel p orbitals. And so you get overlap, but notice in this red area here, the overlap is interrupted. And so this is a weaker type of bond because of that interruption, and this is called a pi bond. And so these are easier to break. They're easier to break because the overlap between the orbitals is interrupted. And so this carbon is an amazing electrophile, first because of the charge, and second because it has a bond that's really easy to break, that pi bond there. Okay. So those are our options. That's the sort of little principle we're going to use as we go through this. And so just to use this first this first exercise A as a comparison, you'll notice that we added carbons, first of all. Right? This molecule on the left has 6 carbons. The molecule on the right has the same 6 carbons in the ring, but then you added 2 more there, so that's 7 and 8. So we added carbons, and that should be like flashing lights that we're going to have to use a Grignard reagent, our carbon nucleophile. Then you would compare it with these two cases, and you'd say, okay, if we look at this molecule, we see the bromine here, so this is where our new carbon chain is going to want to attach. That has 2 carbons, so if this is where our Grignard is going to be attaching, we have the 2 carbons here, and notice the functional group is on the second one. And so that means we're going to use an epoxide to make this transformation happen. Oops. Okay. So we're going to use a Grignard reagent and an epoxide. Now the first thing we have to do is form the Grignard reagent, and we do that by dumping solid magnesium into this. That replaces the bond to a bromine with this almost ionic bond, not quite, but almost ionic bond to the magnesium. This magnesium has really low electronegativity, so it has a positive charge, and the carbon has relatively high, relative to the magnesium, electronegativity, so it has that negative charge, and it's basically going to be able to act like this nucleophile here. That's how it's going to act, with the magnesium and the bromine floating off and doing their own thing. Now we saw that because the functional group is 2 away, that we would use an epoxide. So what we're going to do is make our epoxide here, and these are the 2 carbons that were up here. And notice these carbons here don't have any branches, so we don't have to add any branches down here. We can just react the simplest of all epoxides, name for that 3-membered ring all by itself without any branches, is called oxirane. We can react that with our Grignard reagent. So this attacks one of those carbons. That carbon already had 4 bonds. In order to make room for this new one, it has to break a bond, and the electrons go onto the oxygen. So now we would have this. Here's our carbon 1 and 2. And so that's the molecule we would have at this point. And we're almost there. We just need a hydrogen on that oxygen. And as we've seen in the last exercise, you can make that happen by adding water. Water has those vulnerable, slightly positive hydrogens, and so this oxygen here can just attack one of those, and you would get the OH on that. Okay, so that's the reasoning behind this. Let's just jot down the overall step-by-step thing we did. First thing we did was add magnesium to turn this alkyl halide into a Grignard reagent, carbon nucleophile. Second thing we did was add this 3-member epoxide, oxirane ring. And that reacted with the Grignard reagent to produce something really close to what we wanted. Last but not least, we just had to put a hydrogen on that oxygen, and we did that by adding water. So the answer for this would actually be this right here. Okay, let's jump around just a little bit just to see some consistency between these. So let's compare A with C. Let's try to jump to C. We'll come back to B a little later. So if you look at these, similar process as before, we see that we have 6 carbons on the left, but on the right of the reaction arrow, we have 6, 7, 8, oh my gosh, 9 and 10. We have a whole bunch of other carbons. In other words, we had to form a new carbon-to-carbon bond here to add all these other carbons. And the way we can do that, flashing lights, is with a Grignard reagent. So our first step is to take this alkyl halide, dump some solid magnesium there, and that gives us our Grignard reagent. Magnesium has really low electronegativity, so it's going to be slightly positive, and the carbon it's bonded to is going to be slightly negative. Actually, this will basically function like this. So there we have our beautiful carbon nucleophile. Now, what kind of molecule do we need to add to this? So, whenever you add a Grignard, look to see if your functional group is on the carbon attached to the same carbon that the Grignard attacked, or one carbon away. So here, this was where our Grignard reagent is, and we have 1 and 2 there. So notice the functional group is on 2, and so that's a sign that we would use an epoxide. So we're going to use an epoxide again with this one. Okay, let's think about what epoxide we want. First, I'll just draw the 3-membered epoxide. We know this is 1, we know this is 2. Notice though how 2 here has methyl groups, 2 methyl groups coming off of it. And so I'm going to put 2 methyl groups coming off of that there. Those are these 2. Oops. Here. Okay, so we know the oxygen's slightly negative. We know the 2 carbons are slightly positive. The nucleophile is going to attack the carbon on the left, this number 1 carbon, because it's less crowded. This carbon is bonded to just 1 other carbon, whereas the carbon on the right is bonded to 1, 2, 3 other carbons. So the Grignard reagent, carbon nucleophile, attacks the less crowded carbon. To make room, this bond breaks, the electrons go onto the oxygen, and we have, so these are our 2 carbons. Carbon number 2 has the 2 methyl groups, and now the oxygen got pushed there. It has a full negative charge, and there is where we're at. Now that's pretty close to what we want. We just want the oxygen to have a hydrogen on it, so we can react that with some water. The oxygen and water is slightly negative, the 2 hydrogens slightly positive, and so this can attack one of those hydrogens, and you get the hydrogen there. Okay, so there's all the reasoning. The answer is, first, we had to dump some solid magnesium in here. To make the Grignard reagent. Next, once we have the Grignard reagent, we had to react it with this epoxide right here, which we drew by carefully analyzing the carbon chain. So I'm going to draw that epoxide here. Once we had that, we just had to add a hydrogen onto the oxygen there. So that third step is just adding water as a source of those hydrogens. And those 3 steps together are the answer for this problem. That's how you can make this transformation happen. Alright, let's see another example. How about this one? This is a similar type of thing, but it adds a complication. So first, you notice that in this transformation, this carbon on the left has, or I'm sorry, the molecule on the left has 1, 2, 3, 4, 5, 6 carbons. On the right, we've got 1, 2, 3, 4, 5, 6, 7, 8. If you ever add carbons, that's a sign at this point in the course that you have used a Grignard reagent. So we know we're going to have to use a Grignard reagent. We're going to have to turn this molecule we start with into one. And we can do that by dumping some solid magnesium into there. So we've got this benzene ring, alternating single and double bonds. Once the magnesium gets dumped in there, you'll have magnesium chloride. Now usually this is bromine, but as you see here, it could be chlorine too. Okay, and that really is going to function like this sort of a nucleophile here, because the magnesium has such low electronegativity that it basically gives its electrons away, and the carbon gets both of them. The magnesium and the chlorine would be floating around in the beaker doing their own thing. Okay, well if that's our nucleophile, then we can go over to our product and look and see, okay, if this is the carbon that we're going to be attaching, then the thing we want it to attach to would have 2 carbons. And as we've seen before, if you notice our little functional group thing here is on carbon number 2. And as we've seen before, if the functional group is coming off of carbon number 2, we want to use an epoxide to make that happen. So we want to react this with an epoxide. You draw the 3-membered ring, number the 2 carbons in it, and then look back at that original thing. There are no carbon chains coming off of there, so I don't have to draw any carbon chains coming off of here. So each of these carbons is slightly positive, the oxygen slightly negative. This nucleophile attacks one of those, the bond breaks. These are equally crowded, so it doesn't matter which one it attacks. And so what we'd have here after this step is this molecule here. So notice there's 1, that's 2. Alright, now as usual, we can add some water just to calm things down a little bit. Oxygen slightly negative, hydrogen slightly positive. So this can attack one of those hydrogens, and you're left with this. So that is very close, but not exactly what we wanted, because we have an OH instead of a Cl. And the way you can turn an OH into a Cl is with a molecule called thionyl chloride. That was one of these you'd want here. So SOCl2, and just to make the reaction happen, you also have to add a little bit of a base called pyridine. So Py is standing for that. And so that can replace an OH with a Cl. I won't draw the mechanism for that here, just because it's a little involved, but I'll make a separate video that walks through the mechanism for how that happens if you're interested. You wouldn't have to draw the mechanism for that, but you should know that if you add thionyl chloride, SOCl2, with pyridine, you will turn an OH into a Cl. Okay, so the steps for this are, first, dump some solid magnesium in. That creates your Grignard reagent. Once you have your Grignard reagent, create that new carbon-to-carbon bond. Because the functional group was 2 carbons away, we used an epoxide. And to draw that epoxide, we looked at the branches on that carbon chain. We added some water to get rid of the negative charge on the oxygen. And last but not least, to replace the alcohol with the chlorine, we added thionyl chloride, SOCl2, and pyridine. And so these here would be the answer for this reaction. Okay, let's try G. So with G, what we have is, what we would have here is we see that the molecule on the left has has 1, 2, 3, 4 carbons. The molecule on the right has 1, 2, 3, 4, 5, 6, 7, 8. Oh my gosh, so many more carbons. So at this point in the course, that would be flashing lights telling you that you would want to use a Grignard reagent. Now, you make a Grignard reagent by taking your alkyl halide and dumping some magnesium into it. So here, the rest of the molecule would stay the same, and we just have that there. And really, that would function as this, sort of a carbon nucleophile. And the magnesium and the chloride really are just a counter ion, and they float away once this reaction starts happening, so we can ignore them for now. Okay, well, now we can look at our product, and we can see that if our nucleophile would be right here, that's our Grignard reagent. So the thing we'd want to attach is this. Now, we can see that the functional group here is on that second carbon away, and as we've seen a few times before now, if the functional group is 2 carbons away, you want to use an epoxide. And so here we're going to draw an epoxide, and we want to make sure this epoxide will give us the product we want. Notice here we have 2 carbons coming off of that carbon number 2. So I'm going to draw those 2 carbons there. That resembles these. Okay, so that's our little epoxide. If we react that with our Grignard reagent, the oxygen's slightly negative, the 2 carbons are slightly positive. This nucleophile is going to attack the less crowded area, which is the carbon on the left. The bond breaks, the electrons go onto that oxygen there, and you're left with, so notice, these are our 2 carbons there. The oxygen goes away, and this carbon number 2 has those 2 methyl groups. That oxygen has a full negative charge. And just so we can help see things, keep in mind this was our Grignard reagent. So we formed this new carbon-to-carbon bond. Okay, so that's pretty close actually to what we want. We just want to add that extra hydrogen there, so to get that hydrogen on there to help stabilize or cool off that negatively charged oxygen, we can add a water. So this oxygen here attacks one of those hydrogens, and you get this product. So from the beginning, from the top, the first thing we did was we added solid magnesium. That created our Grignard reagent. Once we had that, we saw that the functional group was 2 carbons away from the Grignard, from where the Grignard was attaching. And because of that, we knew to draw an epoxide. We looked at the branches on that epoxide to draw the correct epoxide. After the epoxide, we just cooled off the oxygen, or I should say calmed down the oxygen by giving it a hydrogen. And so the answer for this one is just those 3 steps: magnesium, the epoxide, and water. Okay, last but not least, let's try this one here, H. And then I'll do the ones we've skipped over or haven't done just yet in a separate video, just so these videos don't get too long. So if you notice here, the molecule on the left has 1, 2, 3, 4, 5, 6 carbons. The molecule on the right has 1, 2, 3, 4, 5, 6, and then 7, 8, 9, 10, 11 carbons. We've added a whole bunch of carbons. That is a sign at this point in the course that you would want to use a Grignard reagent. So the first step is to change this molecule we're starting with into a Grignard. We do that by dumping solid magnesium there. And so we'll have that Grignard, and that Grignard really functions as this nucleophile. So that's what's going to happen there. So if we go back here, this is the place where the nucleophile is and where it's going to attack our other molecule. Now, if you notice, the functional group here is 2 carbons away. It's on that second carbon. And as we've seen several times so far, when that functional group is on that second carbon, you want to use an epoxide. So an epoxide. Okay. So we're going to add an epoxide here. And here this will be carbon number 1, carbon number 2. Notice that carbon number 2 has this sort of funny chain coming off of it, so we'll want to make sure that funny chain is also coming off of our epoxide. Okay. Grignard reagent attacks the less, and I should draw these charges in. So oxygen slightly negative, the carbons are slightly positive. Notice that the carbon on the left is less crowded. It isn't bonded to as many carbons, so that's the one the nucleophile attacks. To form that new bond, it has to break a bond. It breaks the bond to the oxygen. And so you end up getting, if you notice, those are our 2 carbons now. The oxygen was pushed off to the second one. You end up getting this molecule, which is really close to the molecule we want. The only thing is that negative charge on the oxygen, which, as we've seen time and time again, we can remove by adding water. Water here is just a source of hydrogens, so the negative oxygen attacks the hydrogen there, electrons go on to the oxygen, and you get your beautiful product. Alright, so in this, the first thing we had to do was create our Grignard reagent. We do that by, so we saw that the product has more carbons than the reactants. That's what let us knew we had to do, use a Grignard reagent. To make the Grignard reagent, we added magnesium. Once we had it, we had to react it with an epoxide. We knew to do that because the functional group was coming off of the second carbon away from where the Grignard reagent was going to attack. And so we drew the epoxide based on the branches that this had. We had that isopropyl branch there coming off of carbon 2. Once we had that, we just had to add a hydrogen onto the oxygen. We did that by adding water, and so the answer for this would be this thing right here. Okay, so we skipped over several problems and we didn't get to one of them, so I'm going to make another video to go over those. But so far, you could see that you can use these Grignard reagents to make new carbon-to-carbon bonds, and if the functional group at the end of those bonds is 2 carbons away, you can use an epoxide.